In this video, we are going to talk about homogeneous linear systems. So what are these kinds of linear systems? If you take a look at this system of linear equations as shown, we can observe that the sum of this polynomial with n variables, is all 0. So a homogeneous linear system is a system of linear equations whose equations has sum equal to. So in matrix equation, this can be written as a x equal to 0, where a here is the coefficient matrix and x is the column matrix for the variables, and 0 is the sum column matrix for the sum of the linear system. So one thing that is common in homogeneous systems of linear equation is that it is always consistent. From our previous video, we have talked about the three types of solutions to linear systems, and those are inconsistent or no solution, consistent or there is a solution, and dependent systems wherein there is infinitely many solutions. So the augmented matrix of a homogeneous system is shown. So for example, we have here a homogeneous linear system, ax plus by equal to 0, cx plus dy equal to 0. We can write it in matrix equation as ax equal to 0. So we have here the coefficient matrix. This is your column matrix for variables, and these are the column matrix for your constants. From the matrix equation, we can now write the augmented matrix a comma 0 as shown in the figure, or we can write this as a in a vertical line enclosed by a bracket, and this is equal to a, b, c, d. This is for the coefficient matrix, and then you place a vertical line to separate the constants of the system. And here we have your augmented matrix of the systems of linear system, homogeneous linear system. So solutions for homogeneous linear systems are divided into two types. First is the trivial solution, wherein all the variables will be equal to 0. This is also called zero solution. Trivial solution. This happens when r is equal to n. Later we will define what is r and what is n. Second is non-trivial solutions, wherein the values of variables can be non-zero. We can also call this as non-zero solution. Now in this case, for non-trivial solutions, r is less than n. Now what is r and n? R is the number of remaining equations if the system is transformed in row echelon form. And n is the number of variables of the system of linear equations. Later we will demonstrate on how are we going to determine r and n. So let's have an example. Determine if the homogeneous linear system has a trivial or non-trivial solution. Solve for the values of the variables. So we have here a system of homogeneous linear equations. That is because the constants are all 0 in each equation. So let's try to write this one in its matrix equation. Remember, in matrix equation, that would be A, the coefficient matrix, times the column matrix for the variables, and that is equal to 0. 0 matrix, the column matrix for the constants as shown in the system of linear equation. So for A, this would be, we have our coefficients here, 1, 1, negative 1, 2, 4, negative 1, 3, 2, and positive 2. This is our coefficient matrix. The correspondence, you can check it. 1, 1, negative 1, 2, 2, negative 1, 3, 2, and positive 2. You also have your column matrix for the variables, and this is given as x, y, and z. You also have your 0 matrix, 0, 0, and 0. So if you will write this in matrix equation, that would be 1, 1, negative 1, 2, 4, negative 1, 3, 2, and 2. This will be multiplied by x, y, z matrix. And that is equal to the 0 matrix. So from here, we can now write it in its augmented matrix. That would be A, comma 0, or some books write this as A, 0. And this will be equal to 1, 1, negative 1, 0, 2, 4, negative 1, 0, 3, 2, 2, and 0. So that is the augmented matrix of your system of homogeneous linear equations. So let us try to solve this using the ordinary elimination method. I just showed you the augmented matrix of this system. But let's try to solve it using the ordinary elimination method. Take note that we have your equation x plus y minus z equal to 0, 2x plus 4y minus z equal to 0, 3x plus 2y plus 2z equal to 0. I will call this equation 1. This would be equation 2, and we have your equation 3. So using the process of elimination, let's try to eliminate the first variable, that is x, for the second equation. And to do that, we multiply the first equation by negative 2 and add it to the second equation. So this would be negative 2 times x is negative 2x, negative 2 times y is negative 2y, negative 2 times negative z is equal to positive 2z, and this is equal to 0. And then copy the second equation. This would be 2x plus 4y minus z, and this is equal to 0. If you take the sum of these two equations, we will have 0, 0x, or that can be written as 0. This would be positive 2y plus z. This would be equal to 0. Let's try to get rid of this coefficient of the y variable by multiplying the whole equation by positive 1/2. And with that, we will have your equation as y plus 1/2 of z, and that is equal to 0. I will call this your equation 2a. So for the third equation, to eliminate the x variable, let's do a process of elimination by multiplying the first equation by -3. So we have -3 multiplied that by equation 1. This would be -3x minus 3y plus 3z, and this would be equal to 0. And then add equation 3. That would be 3x plus 2y plus 2z. This would be 0. This is -y plus 5z, and this is equal to 0. I will call this equation 3a. And now we have your equations: x plus y minus z equal to 0. That would be the second equation, 2a. Y plus 1/2 of z equal to 0, and you have your third equation here, the modified third equation, -y plus 5z equal to 0. Equation 1, equation 2a, and equation 3a. So now that we have your modified equations, we have eliminated the x variable in the second and third equation. We can now eliminate the third variable for the third equation. And to do that, we will do again the process of elimination. That would be easy because we can just add equation 2a and equation 3a, since y here has opposite signs. So I did not multiply equation 3a by -1 for us to have an easier solution. This would be y plus 1/2 of z equal to 0, -y plus 5z equal to 0. Adding these two equations together, we have 0 plus 11 over 2z, and that is equal to 0. Let's try to multiply this by 2/2 to get rid of the coefficient of the variable z, and that would be z equal to 0. We have obtained your value for z. We can call this equation 3b, the second modification for the third equation. And with this, we can now write your new equations. That would be x plus y minus z equal to 0. We have here y plus 1/2 of z equal to 0, and we have your positive z equal to 0. This is our equation 1, equation 2, and equation, or 2a rather, and equation 3b. So from here, we can write this in its augmented matrix form. Okay, so let me complete these equations. So we can have here an invisible expression or term for the second equation, and that would be 0x, an x variable with a coefficient of 0. This would be positive. We can write here again 0x plus 0y plus z. So we can write this as an augmented matrix that would be 1, 1, negative 1, 0, 0, this coefficient, positive 1, positive 1 half, and 0. We also have here your last equation, 0, 0, and 1, 0. This is the augmented matrix. Notice that this is already in its row echelon form. Okay? So now we can define the variables or the parameters r and n. We have defined r as the numbers of the remaining equations in the row echelon form of the augmented matrix after doing the process of elimination. So this would be, we have here three equations, equation 1, 2, and 3. So this is equal to 3. And if you will determine n, or the number of variables in these equations, we have 1, 2, and 3. This represents the coefficients of x, coefficients of y, and coefficients of z. So this is also 3. And we can say that r here is equal to n. And we have defined that if r is equal to n, the number of remaining equations in REF is equal to the number of the variables, then we can say that this is an example of a trivial, or the homogeneous linear equation would have a trivial solution. So that is a trivial solution. Now let's try to solve that using back substitution. Using back substitution, we have your z equal to 0. Okay, so that is already the value of z. To find the value of y, we can use equation 2a. And that would be y plus 1 half of z. But your z is equal to 0, and that is also equal to 0. We have your y equal to 0. For the value of x, we can use equation 1. That would be x plus y, but y is equal to 0, and minus z, which is also equal to 0. That would be equal to 0. We have the value of your x also 0. And through with the condition here, we have a trivial solution for the homogeneous linear equation. Let's try another example. You're again going to determine the homogeneous system linear equation solution. We are determining if it is trivial or non-trivial. We are going to solve for the values of the variables. We have here a system of linear equations involving 4 equations and 4 unknown variables. So again, let's call this your equation 1, equation 2, and equation 3, and equation 4. So let us first eliminate the first variable in the second and third equation. And luckily for the fourth equation, we don't have to eliminate variable w because that is already not present in your fourth equation. So we can only do elimination in the second and third equation. So let's do that by first multiplying equation by 1 by negative 2. and adding it to equation 2. So we have here negative 2w plus, or negative rather, negative 4x minus 3y times negative 2, that would be positive 6y, and we have negative 8z equal to 0. And just copy the second equation. We have 2w minus 3x plus 5y minus 7z. This is equal to 0. Take the sum of these two equations. We have 0 minus 7x plus 11y minus 15z equal to 0. And let's try to eliminate this coefficient of x by multiplying the whole equation by negative 1 over 7. And we will have now x minus 11 over 7 y plus 15 over 7 z, and this is equal to 0. So let's call this your equation 2a. To eliminate w in equation 3, we will multiply equation 1 by negative 5 and adding it to equation 3. So we have here negative 5w minus 10x plus 15y minus 20z equal to 0. 5w, copy equation 3, plus 6x minus 9y plus 8z, and this is equal to 0. Take the sum of these two equations. We have 0. This would be negative 4x plus 6y minus 12z equal to 0. Let's multiply the whole equation by negative 1/4 to get rid of the coefficient of x. This would be x minus 3/2 of y, and this would be positive 3z equal to 0. I'll call this equation 3a. So we now have your equations. W plus 2x minus 3y plus 4z equal to 0. This would be, the second equation would be x minus 11 over 7y plus 15 over 7z equal to 0. This would be x minus 3/2 of y plus 3 of z equal to 0. And lastly, we have your fourth equation, y plus 12z, that is equal to 0. We have your four equations here: 1, 2a, 3a, and equation 4. The next step is to eliminate the variable x in the third equation by using again the process of elimination. To do that, we will subtract 3a from equation 2a. So this would be x minus 11 over 7y plus 15 over 7z equal to 0, this would be x minus 3 halves of y plus 3z equal to 0. Don't forget that would be a subtraction to eliminate the variable x. This would be x minus x, 0, 11 of negative 11 over 7y minus negative 3 halves of y is negative 1 over 14 of y. This will become 15 over 7z minus 3z is equal to negative 6 over 7z. That is equal to 0. 0 minus 0 is 0. To get rid of this coefficient, we are going to multiply it by negative 14. And by multiplying that, we have your new equation. 0, we have here y plus 12z equal to 0. I'll call this equation 3b. So we have your new equations. That is w plus 3x or 2x. I'm just copying the first equation. Minus 3y plus 4z equal to 0. We have your second equation. Just copy it. X minus 11 over 7y plus 15 over 7z equal to 0. The third equation, the modified, would be y plus 12z. And copying your fourth equation, this is 1, 2a, and 3b. The fourth equation is y plus 12z. So if you will notice, equation 3b and equation 4 are the same. If you are going to do the process of elimination for equations 3b and 4 to get rid of the variable y in the fourth equation, we will arrive with this. I'll demonstrate it. That would be 3b minus equation 4 to get rid of the variable y in equation 4. This would be y plus 12z equal to 0. We have here y plus 12z equal to 0. If we will eliminate this, we will have y minus y 0 or 0y, 12z minus 12z plus 0z, and this is equal to 0. Our equation for A. So in doing this, we have your new equations. That would be w plus 2x minus 3y plus 4z equal to 0. X minus 11 over 7y plus 15 over 7z equal to 0. This would be y plus 12z. And we have your 0z equal to 0. This is equation 1. Equation 2a. Equation 3b. And this is equation for A. Let's try to compute the systems of linear equation by adding coefficients and the other variables with their coefficients. This would be 0w plus 0w plus 0x plus y. And we have here 0w plus 0x plus 0y plus 0z. And from here, we can obtain the augmented matrix of the system of linear equation. That would be 1, 2, negative 3, For the constants, this would be 0. We have 0, 1, negative 11 over 7. This would be 15 over 7. 0. This would be 0, 0, 1, 12, 0, 0, 0, 0, 0, and 0. So this is already in its row echelon form. So if you will count the remaining equations in row echelon form of our system of linear equation, we have 1, 2, and 3. This cannot be considered an equation because that is just 0 equal to 0. So there are a remaining 3 equations in row echelon form, and the number of variables that are required is still 4. We have here 1, 2, 3, and 4. So in this case, r is less than n. And if r is less than n, then this is an example of a non-trivial solution. When we say non-trivial, the answers for the values of the variables can be a non-zero digit. Because if that is a trivial solution, then the answers or the values of the variables should all be equal to 0. Also, we can say that this is an example of a dependent solution. Why is that so? Because if you will revert this back to its equation form, this would be w plus 2x minus 3y plus 4z x minus 11 over z, or 11 over 7y plus 15 over 7z equal to 0, y plus 12z, and we have 0 over 0. So these are the 3 remaining equations. We can say here, in the last equation, the third equation rather, the variable y or variable z, they can assume any value. Take note that I use the word or, because if you assumed a value for y, then you can already compute for the value of z using equation 3. You only need to assume one variable, and with that you can solve for the value of the other variables using the back substitution process. So after assuming a value of y or z, we can compute for z. For example, if you assume the value of y, you can compute for the value of z, and with that you can compute for the value of x and w using back substitution. So there are infinitely many solutions for this example. So let's try to review the concepts that were discussed in this video, and those are: a homogeneous linear matrix in its row echelon form has 2 solutions. The first is a trivial solution, or non-zero or zero solution rather, if the r is equal to n, and it can have a non-trivial solution or a non-zero solution if r is less than n. Thanks for watching.